In 1956, Chien-Shiung Wu cooled a speck of radioactive cobalt to within 0.003 of 1 degree of absolute zero and caught the universe doing something 3 centuries of physics said was impossible. She caught it telling left from right. Every law ever written down had been blind to the difference between a left hand and its mirror image. She proved that the blindness was just an assumption nobody had ever bothered to test, and that underneath it, the universe has a preferred hand built into its foundations since before the first star formed. It was confirmed within weeks. It ran on the front page of the New York Times. But the next year, faster than almost any award in its history, the Nobel Prize for it went to the 2 men who had asked her to look. Her name was not on it. She had chosen the method. She had run the experiment in the cold while one of them slept beside the machine. Therefore, over the 16 years that followed, 18 physicists nominated her 23 times, and the committee said no every single time. When you follow this from a question 2 theorists stumbled onto in a library through the coldest experiment of the decade, past Wolfgang Pauli losing a bet he swore he could not lose, to a medal with the wrong name stamped on it, you are going to understand why this should have been one of the most famous results of the century. So get comfortable and subscribe or join if you have not yet, because this trail does not end at the prize. If you want the longer, stranger versions of stories like this, one, the deeper dives into physics, cosmology, and the people history quietly wrote out of it, that is what the Patreon is for. Stay with it to the end, because the hand the universe chose does not stay inside the cobalt. It reaches forward into the molecules your own body is built from, and into a question physics still cannot answer. Let's ease into it. Hold your hands up in front of your face. Look at them. The left one and the right one are mirror images of each other. Perfect reflections, every curve and knuckle on one matched by the opposite curve and knuckle on the other. And yet, you cannot lay one on top of the other. Turn them however you like. Press the palms together, line up the fingers, rotate them through every angle you can manage, and they will never occupy the same space the way 2 identical objects would. A left hand is not a right hand. It is the reflection of a right hand, which is a different thing, and the difference is permanent. For almost the entire history of physics, that difference was believed to mean nothing to the universe. Not nothing to us. We obviously care which hand is which, but nothing to the actual machinery of reality. The deepest belief in physics, older and more trusted than almost anything else, was that nature itself could not tell the difference between left and right. That if you built a perfect mirror image of any physical process, atom for atom, force for force, the reflection would behave exactly the same as the original. There was no experiment, not a single one in 3 centuries of careful work that could distinguish our world from its mirror image. Sit with what that actually implies, because it is stranger than it sounds. It means the words left and right, as far as the laws of physics were concerned, pointed at nothing real. They were a convention, like deciding which side of the road to drive on. If you wanted to explain to an intelligent creature on a planet 10,000 light years away what you meant by the word left, you could not do it. There was no way. You could send them the laws of physics, every equation we had, and none of it would single out one hand over the other, because every equation worked identically forwards and backwards through a mirror. Left and right were human words for a distinction the universe did not recognize. And then, over 11 days at the end of 1956, a woman named Chien-Shiung Wu took a small amount of radioactive cobalt, cooled it to within 3,000ths of a single degree of the coldest temperature that is allowed to exist, and watched it fall apart. And in the precise way it fell apart, she saw something that nobody had ever seen and almost nobody had thought to look for. She saw the universe choose a side. The cobalt was throwing out electrons, and it was throwing more of them in one direction than the other, and the direction it preferred was a direction that should not have existed. The mirror image of her experiment, the reflection, did not behave the same way. It could not. For the first time in the history of the world, a physical process had been found that told left from right at the most fundamental level there is. That sounds like a small technical thing. It is not. What she had proven is that reality is not symmetric, that somewhere in its foundations, the universe has a preferred hand, built in, structural, not an accident of how things happen to land, but a feature of the laws themselves. And we still, almost 70 years later, do not know why. Nobody knows why. The man who had spent his life as close to this question as anyone admitted, late, that he did not have the imagination to understand what he had been handed. The two men who had asked Chien-Shiung Wu to perform that experiment took the Nobel Prize for it the following year, in 1957, faster than almost any Nobel in the history of the award. Her name was not on it. She had designed the experiment, she had chosen the method, she had run it, checked it, and confirmed it, and her name was not on the prize. And the reasons that has been given for that over the decades are a study all by themselves in how a scientific establishment decides who gets to be remembered. So, there are two broken symmetries in this story, and they are tangled together so tightly that I am not sure you can fully understand one without the other. There is the broken symmetry of nature, the discovery that reality itself prefers one hand, which is one of the strangest facts ever established about the world you live in. And there is the broken symmetry of credit, the discovery that the woman who proved it was written out of her own result. I want to walk you through both, and I want to be honest with you that by the time we get to the end, the handedness Wu found is not going to stay politely inside the nucleus of a cobalt atom. It is going to follow you home. It is in the chemistry that built you. Every protein in your body is made from molecules of a single-handedness, and the universe's preference for one side and your body's preference for one side may turn out to be the same preference, traced back to the same broken mirror. We do not know that they are, but the people who study it cannot rule it out, and that uncertainty is its own kind of vertigo. I want to start with how comfortable everyone was, because the comfort is the part that should bother you. The reason nobody had looked is that looking seemed pointless. And the reason looking seemed pointless is a belief so deep that grown physicists used it to talk other physicists out of even trying. The belief had a name. The technical term is parity. And parity conservation was the principle that the laws of physics are unchanged when you flip space into its mirror image. The idea in its modern form was written down in 1927 by Eugene Wigner, one of the great mathematical physicists of the century. Building on patterns that had been noticed in the light coming off of atoms in the spectra of iron and titanium by spectroscopists named Otto Laporte and Henry Norris Russell, Wigner formalized it. He gave every quantum state a property, a parity that was either positive or negative, like a kind of handedness label, and he showed that in the interactions known at the time, when particles came together and changed into other particles, the total parity of everything before the reaction equaled the total parity of everything after. The label was conserved, it did not change, and because it did not change in any reaction anyone had studied, parity took its place beside the great conservation laws. the conservation of energy, the conservation of momentum, the conservation of electric charge, the small handful of absolute accountancy rules that the universe was believed to obey without exception. Here is what I want you to understand about how that belief functioned, because this is where it stops being a story about equations and becomes a story about people. Parity conservation was not just a result, it was an intuition that felt like common sense, and the intuition came first. The historian of physics, Alan Franklin, who has written more carefully about this episode than almost anyone, summarizes the attitude of the era in a single question that physicists genuinely found persuasive. Why should nature distinguish between left and right? Why would it? What possible reason could the universe have to care which hand you held up? It seemed obvious that it could not, and the obviousness did the work that evidence is supposed to do. The Nobel Committee itself, when it later described all of this, said the symmetry of left and right had been assumed, and I want you to hear the exact word they used, almost tacitly, almost without being spoken. It was so deep that it lived underneath the level of things you say out loud. And it had been confirmed. That is the part that makes it defensible. In the interactions that were well understood, parity really was conserved, and it had been checked. The force that holds atomic nuclei together, the strong force, conserved parity, and you could measure that. The electromagnetic force, the force that governs light and chemistry and electricity, conserved parity, and you could measure that to extraordinary precision. So when physicists generalized from those forces to all forces, they were not being lazy. They were doing what science usually rewards you for doing. They were taking a principle that held everywhere they had looked and assuming it held everywhere. The trouble is, the word everywhere. They have not looked everywhere. There was a fourth way that particles interact, and in that fourth way, nobody had checked at all. The four fundamental forces are the four basic ways anything in the universe can push or pull or transform anything else. There is gravity, which you feel every second. There is electromagnetism, which lights your screen. There is the strong force, which binds the cores of atoms. And there is the weak force, which is the strangest of the four and the one almost nobody outside of physics has heard of, and it is the weak force that is going to break everything open. The weak force is the force responsible for a particular kind of radioactive decay, the kind where a neutron inside a nucleus turns into a proton and spits out an electron, a process called beta decay. It is slow, it is feeble, it operates only across distances smaller than the nucleus itself. And for our purposes, the crucial fact about it is this. As of the middle of 1956, the question of whether the weak force conserved parity had never been tested. Not once, not poorly, not inconclusively. It had simply never been done, and almost nobody had noticed that it had never been done, because the assumption was so total that the gap in the evidence was invisible. That is the setup. A pillar of physics, trusted absolutely, propping up a corner of the building where no one had ever checked whether there was a pillar at all. And the thing that finally made someone look was not a grand philosophical crisis. It was a small, maddening puzzle about two particles that refused to make sense, and the puzzle had been driving physicists quietly insane for several years. The two particles were called, at the time, the tau and the theta. I want to be careful here, because the tau in this story is not the heavy electron that physicists today call the tau lepton. This is older language from the early 1950s. And these two objects, the tau and the theta, were a genuine headache. They appeared in cosmic ray collisions and in the new particle accelerators. And when physicists measured them, the two particles looked identical in every way that could be measured. The same mass, down to the precision the instruments allowed, the same lifetime before they decayed, the same electric charge, the same spin, by every standard that physics used to decide whether two things are the same thing. The tau and the theta were the same thing, except for one detail. They died differently. When the theta particle decayed, it broke apart into two lighter particles called pions. When the tau particle decayed, it broke apart into three pions. And here is the trap, the thing that turned a curiosity into a crisis. Because of the rules of parity, the rules Wigner had written down, a state of two pions and a state of three pions have opposite parity. One is positive, one is negative. The two-pion ending and the three-pion ending carried opposite-handedness labels. A physicist named Richard Dalitz had worked out a careful method, now called the Dalitz plot, that confirmed it. The decay products had opposite parity, and that was not in doubt. So you had a contradiction with no escape. If parity is conserved, which everyone believed with their whole chest, then a particle that decays into two pions must have started with one parity. And a particle that decays into three pions must have started with the opposite parity, which means the tau and the theta must be two different particles because they end up on opposite sides of the parity ledger. But every other measurement screamed that they were the same particle, same mass, same lifetime, same charge, same spin. You could keep parity, or you could keep your sanity about what makes two particles identical. But in 1956, you could not keep both. That is the kind of problem that ruins careers and dinner parties. And it came to a head in April of 1956 at a conference held every year in Rochester, New York, where the world's particle physicists gathered to argue. The tau and theta puzzle was the dominant topic. And during one of the sessions, a physicist named Martin Bloch, who was sharing a room at the conference with Richard Feynman, put a question to Feynman that he was too junior to ask the room himself. Bloch's question was heresy. What if, he asked, the tau and the theta really are the same particle, and the reason it can decay into states of opposite parity is that parity simply is not conserved in this kind of decay? What if the sacred law just does not hold here? Feynman, who was not too junior to ask anything, raised it for him in the open session, and the reaction in the room tells you everything about the grip the assumption had. The idea was not refuted. It was not even seriously engaged. It was treated as the kind of thing you say out loud only because someone has to say the obviously wrong thing so the smart people can move past it. Parity violation was not a hypothesis. It was a faux pas. Feynman would later recall that he himself did not take it seriously enough to pursue, and he would spend years mildly haunted by how close he came. But two people in that broader conversation did take it seriously, and they took it seriously in the most dangerous way possible, which is that they decided to go check whether the assumption had any evidence behind it at all. Their names were Tsung-Dao Li and Chen Ning. Li was at Columbia University, not yet 30 years old, a prodigy who had come from China through the University of Chicago. Yang was a few years older, also Chinese-born, working between the Institute for Advanced Study at Princeton and Brookhaven. They had collaborated for years, and in the summer of 1956, they did something that sounds almost too simple to be the turning point of the story. They went to the library. They sat down and they asked a question that nobody had thought to ask in 30 years. Where exactly is the experimental evidence that parity is conserved in the weak interaction? Not in the strong force where everyone knew it held. Not in electromagnetism, where everyone knew it held. In the weak force specifically, the force responsible for beta decay, where the tau and the theta were tearing the rulebook apart. They combed the literature, and what they found, or rather what they failed to find, is one of the quietly devastating moments in 20th century physics. There was nothing. There was no evidence at all. The conservation of parity in the weak interaction had never been tested. Every physicist alive had assumed it, taught it, built on it, and not one of them had ever performed the measurement, because the measurement seemed unnecessary, because the assumption felt like common sense. As one later account of the episode put it, there was not a shred of evidence that the weak interactions conserved parity. For more than 20 years, people had simply assumed it without checking. I need you to feel the weight of that, because it is the first place in this story where the floor drops out. This was not fringe physics. This was the foundation. And the foundation, it turned out, had never been inspected. The whole structure was standing on an assumption that everyone trusted precisely because everyone else trusted it, a belief held up by nothing but its own popularity. And the people whose entire profession was the relentless interrogation of nature had, on this one question, simply declined to ask. Li and Yang wrote it up. The paper was received by the journal Physical Review on the 22nd of June, 1956, and it was published on the 1st of October that year, in volume 104, beginning on page 254. The title was a question which is unusual for a physics paper and tells you they knew exactly how provocative they were being. It was called Question of Parity Conservation in Weak Interactions, and the paper did not claim that parity was violated. That is important, and it is a part of the story that gets flattened later. Li and Yang did not prove anything about the universe. What they proved was about physics itself, about the discipline. They proved that the discipline had been asleep. They demonstrated, with citations, that the belief was untested. And then they did the genuinely useful thing. They laid out a menu of specific experiments that could actually test it. One of those proposed experiments was the measurement of beta decay from a radioactive nucleus whose spin had been lined up in a single direction, to see whether the electrons came out symmetrically or whether they showed a preference. That proposal is the seed of everything that follows. And here is the detail that should genuinely disturb you, because it deepens the negligence from an oversight into something closer to a pattern of not seeing. The evidence had actually been there decades earlier and had been walked past. In 1928, three physicists named Cox, McElrath, and Carolmeyer had done an experiment scattering beta decay electrons, and their data, looked at with the right eyes, showed exactly the asymmetry that signals parity violation. A year or two later, another physicist, Carl Chase, saw the same kind of effect. Nobody understood what they were looking at, not the experimenters, not the readers, not the community. The result sat in the literature for nearly 30 years. A photograph of the answer, developed and printed and filed. And no one recognized the face in it. It was only after 1957, after everything broke open, that a physicist named Lee Grodzins went back and realized those old experiments had seen it all along. The universe had left its handedness lying out in the open since 1928, and the entire profession had managed not to look at it because they already knew, with the certainty that needs no evidence, that there was nothing there to see. That is the soil this discovery grew in, a field so sure of its symmetry that it had ignored its own data for a generation. And into that field, in the spring of 1956, walked the one person stubborn enough and skilled enough to actually do the experiment that everyone else considered a waste of time, to understand why it had to be her, and to understand what it would cost her. You have to know where she came from. Because the woman who would prove that the universe prefers one hand had spent her whole life being told, in 100 different ways, that she had been born on the wrong side of a different symmetry entirely. She was born on the 31st of May, 1912, in a small town called Luhe, near Shanghai, in the years just after the last Chinese emperor fell, and the country began tearing itself between the old world and whatever was coming next. Her name was Wu Chien-Shiung, and the most important fact about her childhood is a fact about her father. Wu Zhongyi was an engineer and a social reformer, and at a time when most girls in China received no formal education at all, he founded a school for them. He built it, the Mingde Women's Vocational Continuing School, in a country and a century where the education of girls was widely considered a waste of resources at best and a danger to the social order at worst. His daughter was one of its first students. The woman who would one day be erased from the most important experiment of her career learned to read in a school that existed only because her father refused to accept that girls did not need to. I want you to hold on to that, because the irony of it is going to sit underneath the rest of this story like a stone. The whole arc of Chien-Shiung Wu's life is the arc of a person whose father gave her, against the entire weight of her society, the conviction that her mind was worth developing, and who then spent her professional life inside an institution, Western physics, that kept finding new ways to tell her it was not worth crediting. She started inside a deliberate act of inclusion and ended inside a quiet act of exclusion. And she traveled the whole distance on the strength of being, by the accounts of nearly everyone who worked with her, simply better at the experiment than the people around her. She was at the top of her class everywhere she went. The girls' school, then a teacher training school, then National Central University in Nanjing, where she finished first in physics in 1934. A mentor urged her to go abroad, to America, where the real work in nuclear physics was happening. And in 1936, she boarded a ship and crossed the Pacific to California, intending to study at the University of Michigan. She never made it to Michigan. She stopped in Berkeley, visited the radiation laboratory, met the physicists working there, and decided this was where the future was being built. She was right. She enrolled at the University of California at Berkeley and went to work in the orbit of Ernest Lawrence, who had invented the cyclotron, the machine that smashed particles together to see what they were made of, and who would win the Nobel Prize for it in 1939. At Berkeley, she worked closely with Emilio Segre, an Italian physicist who would also go on to a Nobel. And Segre left behind a description of her that people still quote, partly because it is generous, and partly because of the particular way it manages to be a little condescending even while praising her. He called her the most talented and most beautiful experimental physicist he had ever met. You can decide for yourself how to feel about a senior colleague filing a young woman's beauty alongside her talent in the official record of her abilities. What is not in dispute is the talent. She earned her doctorate in 1940. And then, despite recommendations as strong as a young physicist could hope for, she could not get a faculty job. American universities in 1940 did not hire Chinese women to teach physics. The barrier was not subtle, and nobody pretended it was about her work. So she taught where she could, at women's colleges, at Princeton, briefly as the first woman ever to teach in the physics department there. And then, in 1944, she was brought to Columbia University to work on the Manhattan Project, the secret American program to build the atomic bomb. She is believed to have been the only Chinese person involved in the project, and it is here that one of the strangest small miracles of her career happened. The kind of thing that, if you put it in a novel, an editor would tell you to cut for being too neat. In the autumn of 1944, The first full-scale plutonium production reactor, the B reactor at Hanford in Washington state, was switched on. It started up, ran beautifully for a few hours, and then began to die. Its power output sagged and faded as if something was strangling it from the inside. And then, hours later, it would mysteriously recover, only to die again. The greatest physicists of the age, including Enrico Fermi himself, the man who had built the world's first nuclear reactor, were baffled. Something was poisoning the reaction, absorbing the neutrons that were supposed to sustain it, but they did not know what. And Segre remembered that his former student, Chien-Shiung Wu, had done her doctoral work on exactly this kind of problem, on the radioactive isotopes of an element called xenon. They pulled her in, and Wu's earlier work pointed directly at the culprit, a particular form of xenon, xenon-135, which is produced as the reactor runs, and which devours neutrons with an appetite that is almost unbelievable. An isotope so greedy for neutrons that a vanishingly small amount of it can choke a reactor the size of a building. She had, in effect, solved the problem before it happened. In a thesis she had written years earlier, on a topic nobody had connected to bombs. The most consequential weapons program in human history was briefly stopped cold by a mystery, and the mystery was solved by a young woman who could not get hired to teach. She stayed at Columbia after the war. By the early 1950s, she was the person you went to when you needed a beta decay experiment done correctly. And correctly is the operative word, because beta decay experiments were notoriously treacherous, full of subtle errors that could fool you into seeing things that were not there or missing things that were. Her reputation was for an almost ferocious precision. There is a line from the physicist Maurice Goldhaber that captures the regard she was held in, half compliment and half complaint. He said that people avoided doing experiments in beta decay simply because they knew that Wu would do a better job than anybody. She was, in the small and brutal world of experimental nuclear physics, the best in the world at this specific, difficult thing. There was a cost running underneath all of it, and it is a cost I do not want to rush past, because the framework of this story is about broken symmetries, and this is one of the deepest. When the communists took power in China in 1949, the country closed behind her. Her father had told her not to come back. She became an American citizen in 1954, and she did not see her family again. She could not return until 1973, and by the time she was finally able to go home, her parents were dead. Their graves had been destroyed in the upheavals of the Cultural Revolution, and a brother and an uncle had been killed. The woman who proved the universe is not symmetric spent her entire adult life on the wrong side of a barrier she could not cross, separated from the people who had made her. And that separation is going to become unbearably concrete in just a moment because of a decision she made in the spring of 1956. Here is how the experiment began. Sometime in the early spring of 1956, before the Li and Yan paper was even published, Tsung-Dao Li came to Wu's office on the 13th floor of the Pupin Physics building at Columbia. They were colleagues at the same university. Li was thinking about Parity, about the menu of experiments he and Yang were assembling, and he wanted to talk to the person who understood beta decay better than anyone he knew. He described the problem. He mentioned a few possible ways one might test for parity violation, and Wu, listening, immediately understood something that Li, a theorist, could appreciate but could not have engineered. She knew exactly which experiment would work, and she knew how to do it. She wrote about that moment years later, and her own words are worth hearing because they carry the particular frustration of someone who had watched the field talk itself out of curiosity for years. She wrote that people had not only taken parity conservation for granted in all interactions, but that this untested notion had actually been used to discourage others from doing any experiments to test it, much less challenge it. The assumption had become a wall against its own examination, and she described her reaction to Li's problem as the reaction of someone who has been waiting without knowing she was waiting. She wrote that this was a golden opportunity for a beta decay physicist, and she asked herself how she could possibly let it pass. Notice what is happening here, because the popular version of this story gets it backwards. The popular version is that Li and Yang had a brilliant idea, and Wu was the technician who carried it out for them. That is not what happened. Li and Yang proved that the question was open. They proposed, in general terms, that someone might test it with aligned nuclei. But it was Wu who proposed the specific experiment, the actual physical method that would become the historic measurement. She was the one who said the best bet would be to take cobalt-60 and polarize it by a technique called the demagnetization method. The choice of cobalt, the choice of how to align it, the entire architecture of the thing that would break parity came from her. Yang himself, years later, would credit her with what he called a deep perception of why parity had to be tested. The conceptual leap of asking the question belonged to Li and Yang. The conceptual leap of how to answer it belonged to Wu. And it is the second leap that the Nobel Committee would treat as though it were merely turning a crank. Now I have to tell you what she gave up to do it, because this is the moment where the broken symmetry of her personal life and the broken symmetry she was about to discover cross each other directly. Wu and her husband, the physicist Lu Yuan, had planned a trip. They were going to sail to Geneva for a physics conference and then continue on to the Far East, to Asia, to China. It would have been Wu's first chance to go home in 20 years. 20 years. 2 decades since she had stepped onto that ship in 1936. The chance to see the country she had left, possibly to see family. The first opening in the wall that had closed behind her. She cancelled it. She let her husband go alone. And she stayed in New York because she understood, correctly, that if she waited several months for the trip, someone else might do the parity experiment first, and she was not willing to risk it. She wrote, with a clarity that is almost painful, that she had to do the experiment immediately before the rest of the physics community recognized how feasible it was and beat her to it. So she traded the journey home for the chance to look at the universe's hidden hand before anyone else could. She gave up the wall coming down for an experiment in the cold. And the experiment was going to require a cold deeper than almost anything human beings had ever produced, because the universe does not surrender this kind of secret at room temperature. To understand why the cold mattered, you have to understand what the experiment was actually trying to see. And it comes down to a single comparison. A cobalt-60 nucleus is radioactive. It undergoes beta decay, which means that inside it, a neutron converts into a proton and throws out an electron. And that electron goes flying off into the world. The nucleus also has a property called spin, which you can picture, roughly, as the nucleus rotating, giving it an axis, a direction it points, like the axis of a spinning top. Wu's question was beautifully simple to state. When the cobalt nucleus throws out its electron, does the electron come out evenly in all directions relative to the spin axis, or does it prefer to come out one way, along the spin or against it? If the electrons come out symmetrically, with as many heading toward the north pole of the spin as toward the south pole, then parity is conserved, and the mirror image of the experiment looks the same as the experiment. But if the electrons prefer one end, if more of them come out against the spin than along it, then you have found something the mirror cannot copy. Because spin and motion behave differently under reflection. When you reflect the whole experiment in a mirror, the direction of the electron's motion flips, but the direction of the spin does not flip the same way. The technical statement is that spin is what physicists call an axial vector, and momentum is a polar vector, and they transform differently under reflection, but you do not need the jargon to feel the result. If the real cobalt prefers to shoot electrons against its spin, then the mirror cobalt would have to prefer to shoot them along its spin, and those are physically different situations. The reflection would be a world that does not exist. The experiment would distinguish left from right. As Wu and her collaborators wrote in the paper, if an asymmetry in the distribution is observed, it provides unequivocal proof that parity is not conserved in beta decay. Unequivocal. That is a strong word for a physics paper, and they chose it on purpose. So the whole thing comes down to lining up the spins of the cobalt nuclei so they all point the same way, and then counting electrons at each end. And that is where the trouble starts, because nuclei do not want to line up. At ordinary temperatures, atoms are a chaos of thermal motion, jittering and tumbling, and any attempt to align their nuclear spins is instantly destroyed by the heat. The way a magnet cannot hold a crowd of people facing one direction if they are all running around at random. To freeze the nuclei into a single orientation, you have to remove almost all of the thermal motion. You have to make it cold. Not winter cold, not the cold of liquid nitrogen, which deep freezes flesh in seconds. You have to go down to within a hair of absolute zero, the temperature at which motion itself nearly stops, the coldest anything is allowed to be. Wu's own laboratory at Columbia could not reach those temperatures. This kind of cold was its own specialty, a dark art practiced in only a few places in the world. And so Wu did something that the lone genius version of scientific history tends to forget. She built a team. On the advice of colleagues, she contacted the National Bureau of Standards, the United States government's measurement laboratory in Washington, where there was a low-temperature group that could produce the cold she needed. And the experiment that broke parity was, from that point on, a collaboration of 5 people. Wu, from Columbia, and 4 from the Bureau of Standards. Ernest Ambler, a physicist whose own training had involved the cooling and orienting of cobalt nuclei, which is precisely why Wu needed him. Raymond Hayward, Dale Hoppus, and Ralph Hudson. I am naming all 5 because the question of who deserved credit for this experiment is the open wound at the center of this story, and you cannot think clearly about that question if 4 of the 5 people are blurred into the word collaborators. They were Wu, Ambler, Hayward, Hoppers, and Hudson, and they ran the thing together in the cold rooms of a government lab through the end of 1956. The cooling method was called adiabatic demagnetization, and the physical setup was as delicate as anything in experimental physics at the time. The cobalt-60 was deposited in an extremely thin layer, a film only about 50 millionths of a meter thick, on the surface of a single crystal of a paramagnetic salt with the unwieldy name cerium magnesium nitrate. That salt was the engine of the cooling. You magnetize it strongly, which lines up its internal magnetic structure, and in doing so lets it shed heat. Then you remove the heat and switch off the magnetic field. And as the salt's internal structure relaxes back into disorder, it pulls heat out of everything touching it, including the cobalt, dropping the temperature far below anything mechanical refrigeration can reach. With this method, they brought the cobalt down to roughly 0.003 of 1 degree above absolute zero. I want to give you that number in a way you can hold. Absolute zero is about -273 degrees on the Celsius scale, the floor of temperature, the point past which you cannot go. They were sitting 3/1000ths of a single degree above the floor of reality. The deep cold of empty space, far from any star, is more than 100 times warmer than the place where they put that cobalt. And the cold would not hold. That is the detail that turns the experiment from a measurement into an ordeal. Once they demagnetized the salt and the cobalt fell to that temperature, heat immediately began to leak back in from the surrounding world, and the whole frozen alignment would survive only for a matter of minutes before warming up and dissolving back into chaos. Every run was a race. They had a brief window, after the cooling and before the warming, in which the nuclei were aligned and the electrons could be counted. And then the window slammed shut and the entire apparatus had to be warmed, regreased, reassembled, and cooled all over again, a process that took 6 to 8 hours for a window of minutes. Dale Hobbs, the youngest of them, slept in the laboratory beside the cryostat because the experiment ran around the clock and someone had to be there when the cold was ready. Hudson would say later that it was an outrageous experiment to even attempt, and that it was surprising it worked at all. They needed one more thing to trust their own eyes, and the way they got it is a small piece of experimental genius that I think deserves more attention than it gets. The problem with any asymmetry measurement is that you can fool yourself. Maybe the electrons look like they prefer one direction, not because of physics, but because your detector is more sensitive on one side, or because the nuclei were not really aligned as well as you thought. You need an independent check that the nuclei actually were polarized, and you need it to come from physics you already trust. So they used the gamma rays. Cobalt-60, after it beta decays, emits gamma rays, and those gamma rays come from the electromagnetic force, which everyone already knew conserved parity. The pattern of gamma rays coming off aligned nuclei would tell them, through trusted physics, exactly how well aligned the nuclei were. The gamma rays were the honest witness. If the gamma anisotropy showed strong alignment, then they knew the polarization was real, and any asymmetry in the electrons was not an artifact. They measured a gamma anisotropy of about 60%, which told them the nuclei were beautifully aligned. The electrons, meanwhile, were detected by a thin crystal of anthracene, a scintillator that flashes when an electron strikes it, mounted a couple of centimeters above the cobalt, with the flashes carried out of the cold by a long light pipe, more than a meter in length, up to a photomultiplier that counted them one by one. So now you have the whole machine, a speck of radioactive cobalt frozen to 3/1000ths of a degree above the bottom of the universe, its nuclei lined up like a field of compass needles, all pointing one way, a crystal overhead flashing each time an electron escapes, gamma rays standing witness to the alignment, and a team of 5 people working in shifts against a clock that gives them minutes at a time. And the question hanging over all of it, the question that had never once been asked of the weak force in the entire history of physics: does the electron care which way the spin points? On the 27th of December, 1956, they had their answer. The electrons were not coming out symmetrically. They were coming out preferentially in the direction opposite to the nuclear spin. There were more electrons heading against the spin axis than along it, and the difference was not small, not a marginal statistical lean that you would have to argue about. It was large, and to make sure they were not being fooled by some stray magnetic effect, they reversed the magnetic field, flipping the direction the nuclei pointed, and the asymmetry flipped with it. exactly as real parity violation would, and exactly as an artifact would not. The mirror image of the experiment did not exist in nature. The universe, in the death of a cobalt nucleus, was telling left from right. Wu, in describing the size of the effect, used a word that physicists almost never use about their own results because it sounds unscientific. She said it was huge. The asymmetry parameter, the number that captures how lopsided the emission was, came out close to -1, which in this context means nearly the maximum possible. The universe was not slightly biased. It was not breaking the mirror symmetry by some tiny correction at the edge of measurement. It was breaking it as hard as it is possible to break it. The weak force, it turned out, does not merely prefer one hand, it is built almost entirely out of one hand. And this is a thing I want to flag now and return to, because it is going to matter at the end. The handedness Wu found is not a faint thumb on the scale, it is total. And the preference that total, written into the foundations of physics, is the kind of thing that does not stay in the nucleus. A bias that deep tends to leave fingerprints on everything built on top of it, all the way up the ladder of matter, all the way up to the molecules that decided which shape life would take. We will get there. There is a human moment buried in those days that I find almost unbearably specific, and it is the kind of detail the framework I am working from would tell you to slow down for. So I will. On Christmas Eve, 1956, in the middle of the experiment, Wu needed to get from Washington back to New York. The airport was closed by snow. She took the last train, riding through the storm on Christmas Eve while the rest of the country was home, carrying in her head the first signs of one of the most important results in the history of physics. When she reached Lee, she told him the asymmetry was reproducible and huge, close to -1. And Lee, the theorist, recognized immediately what the number meant. He told her it was very good, that it was exactly what one should expect for a two-component theory of the neutrino, a piece of deep theoretical structure that the experiment was now confirming. The number she carried through the snow was not just an asymmetry, it was a window into the architecture of the most elusive particle in physics. They did not let themselves believe it right away, which is the mark of good experimentalists and is also the reason the credit story is so painful, because the care she took is exactly the care that gets called merely technical. For 2 more weeks, they hunted for every possible error, every artifact, every way the universe might be lying to them through a flaw in the apparatus. It was not until around 2 in the morning on the 9th of January, 1957, after they had finally convinced themselves the effect was real and not an artifact, that they allowed themselves to mark it. Ralph Hudson produced a bottle of wine, and they drank it from paper cups in a government measurement laboratory in the middle of the night. 5 people who had just become the first human beings to watch the universe distinguish left from right. There was no announcement yet, no headlines, just 5 people, paper cups, and a fact about reality that nobody else on Earth knew. The fact was this: the mirror is broken. It had been broken since the beginning of the universe, and it would stay broken. And from now on, the words left and right were no longer empty conventions. They pointed at something real, something the cosmos itself observed. And the strangest part, the part that even the people in that room did not yet fully grasp as they raised their paper cups, was that nobody had any idea why they had found that the universe prefers a hand. They had not found a single reason for it to. There was no deeper law that demanded it, no principle from which it followed, no answer to the child's question of why this way and not the other. There still is not. We are about to watch the rest of physics scramble to absorb the result, and we are going to watch the discovery move faster toward a Nobel Prize than almost any discovery ever has. And underneath all of that motion, the actual question, the why, is going to sit there untouched, the way it sits there untouched today. The result did not stay secret for long, and the way it got out is one of the great stories in physics, because it shows you how fast the impossible becomes ordinary once one person has done it. Every Friday at Columbia, there was a lunch, an informal gathering of physicists, sometimes called the Chinese lunch, because Lee often chaired it and chose the restaurant. On Friday the 4th of January, 1957, days before Wu's team had even finished convincing themselves, word of the cobalt result was shared at that lunch, and sitting at the table was a physicist named Leon Lederman, who would later win his own Nobel Prize, and who realized in that moment that if parity was violated in cobalt beta decay, it should also show up somewhere else, in the decay of a particle called the muon, which he happened to have the equipment to study at the Nevis cyclotron up the Hudson River. What happened next is the part that should make you uneasy on Wu's behalf, even though the people involved did nothing wrong. That evening, Lederman called his colleague Richard Garwin, and together with a graduate student named Marcel Weinrich, they reconfigured an experiment over the weekend. Not over months, over a weekend. By the early hours of one morning they had it, a clean signal of parity violation in muon decay, an effect so large and so obvious in their apparatus that there was no ambiguity at all. Garwin would describe getting the answer in a single night of work. Wu's team had spent half a year building the cold, fighting the apparatus, sleeping beside the cryostat, and chasing every artifact for 2 more weeks. Garwin and Lederman, knowing what to look for because Wu had already found it, got a confirming result in a weekend. And that gap, the half year against the weekend, is going to echo in everything that follows, because the speed of the confirmation made the original measurement look easy in retrospect. And nothing distorts the assignment of credit like making a hard thing look easy after someone else has done it first. There is a detail here that matters, and it speaks well of Lee. Garwin and Lederman, with their fast and clean result in hand, were in a position to rush into print. Lee dissuaded them from publishing first. He told them it would not be fair to the Bureau of Standards team, to Wu and the others who had done the original and far harder work. So the papers were held and submitted together. On the 15th of January, 1957, both papers went to physical review on the same day. Wu and her 4 collaborators in one, Garwin, Lederman, and Weinrich in the other, and they were published back-to-back the following month, in volume 105, on pages 1413 and 1415. A third confirmation, from Jerome Friedman and Valentine Telegdi in Chicago, followed shortly after. The reason I am giving you all 3 is that the existence of 3 near-simultaneous experiments is going to become, later, one of the arguments for why no single experimentalist could be singled out for the prize. Hold that thought. It is a real argument, and it is also, I think, an incomplete one, and we will weigh it properly. On the same 15th of January, Columbia University held a press conference. The institution understood that something enormous had happened, and the next morning, the 16th of January, 1957, it was on the front page of the New York Times. The headline, as it has been recorded, announced that a basic concept in physics had been reported upset in tests. A basic concept upset. That is newspaper language for the fall of a law that had stood for 30 years. For a brief moment, the violation of parity was not buried at all. It was front-page news, and the public was told, more or less accurately, that physicists had discovered the universe is not the same in a mirror. So I want to be fair and precise here, because the invisible scandal in this story is not that the discovery was ignored. It was not ignored. It was celebrated. The scandal is narrower and stranger than that. It is about whose name got attached to the celebration and whose did not, and how quickly the woman at the center of it was edited toward the margins of her own result. But before we get to that, I want to give you the reaction of the physicists, because their shock is the best evidence of how impossible this had seemed. And one reaction in particular has become legendary for good reason. Wolfgang Pauli was one of the most formidable theoretical physicists alive, a man so feared for his sharp tongue that a wrong idea was sometimes said to be not even wrong, a phrase he coined. Pauli did not believe parity could be violated. On the 17th of January, 1957, not yet knowing that the experiment had already given its answer, he wrote a letter to a colleague, the physicist Victor Weisskopf, and in that letter he wrote a sentence that physicists have been quoting ever since. He wrote in German that he did not believe the Lord is a weak left-hander, and he declared himself ready to bet a very large sum that the experiments would give a symmetric result. He was that certain. He was willing to wager heavily that the universe would turn out to have no preferred hand. And then the news reached him. The experiments had not given a symmetric result. The Lord, it appeared, was exactly the kind of left-hander Pauli had refused to believe in. Pauli's response, in a follow-up note, was almost childlike in its shock. He wrote, again in German, that it was very exciting. And then he asked, "How sure is the news? How sure is the news?" One of the sharpest minds in physics, reduced to asking whether the impossible thing was really, certainly true. Wu herself told a version of the story years later in which Pauli, relieved that no one had actually taken his bet and held him to it, remarked that he could afford to lose his reputation, but he could not afford to lose his money. He had been wrong, completely and publicly wrong, about one of the most fundamental questions you can ask about reality. And he knew it, and the speed with which the wrongness arrived is a measure of how unthinkable the result had been the day before. He was not alone. Richard Feynman, who had nearly chased the idea himself the previous spring and then let it go, had bet against parity violation as well, offering 50-to-1 odds on $1 that it would not be found. He lost, and he paid. The physicist Felix Bloch is said to have told his colleagues at Stanford that he would bet his hat that parity was conserved, and afterward remarked to Lee that he was lucky he did not own a hat. The entire profession had been so sure that an entire informal economy of losing bets sprang up around the result. Grown physicists wagering their reputations and their pocket money on a symmetry that the universe had quietly abandoned at the beginning of time. And then there is Freeman Dyson, another of the towering theorists of the century, whose reaction I find the most honest and the most haunting of all of them, because it is not about the bet. It is about the failure of imagination. Lee and Yang's paper had been sitting in the literature since October. Dyson had read it. Anyone could have read it. The question was right there, open, with the experiments laid out. And Dyson, looking back, confessed his own blindness without flinching. He said that he had read the paper and had not the imagination to say to himself that if this is true, it opens up a whole new branch of physics. And then he indicted the entire field along with himself. He said that other physicists, with very few exceptions, were at that time as unimaginative as he was. That is a remarkable thing for a great physicist to put on the record about himself and his peers. The answer was lying in the open. The question had been asked clearly in print, and the collective imagination of the discipline could not rise to take it seriously until one experimentalist in a cold room forced the issue. That is the abdication, stated by the people who abdicated, The smartest physicists in the world either bet against the truth or lacked the imagination to see that the truth was even worth chasing. And the gap between their failure and her success is precisely what makes the next part so hard to stomach. Because the Nobel Prize moved with a speed that is almost without precedent. Li and Yang's paper was published in October of 1956. Wu's experiment confirmed it at the start of 1957. And in the autumn of 1957, the same year, Li and Yang were awarded the Nobel Prize in Physics for what the committee called their penetrating investigation of the Parity laws, which had led to important discoveries regarding the elementary particles. From foundational paper to Nobel Prize in roughly 13 months, the committee almost never moves that fast because it usually wants to see a result confirmed and absorbed and stress-tested over years before it commits the prize to it. The reason it moves so fast in this case is that the result had been confirmed, overwhelmingly, immediately, by experiment. The theory was vindicated at lightning speed precisely because the experiment was so clean and so decisive. The prize was given that quickly because of the strength of the experimental confirmation. And the experiment that provided that confirmation, the cobalt-60 measurement that turned a provocative question into an established fact about the universe, had been designed, led, and verified by Chien-Shiung Wu. The thing that made the prize possible so fast was the very thing the prize left out. Li and Yang, to their credit, did not pretend otherwise in the moment. At the ceremony, they acknowledged her. In his Nobel lecture, Yang described the experiment plainly as having been conducted by a team led by Chien-Shiung Wu. Led by, the men receiving the prize stood in Stockholm and named the woman who had run the experiment their award was built on. And she was in the audience, and her name was not on the medal. I want you to hold the image of that, because it is the exact center of the broken symmetry of credit, the reflection and the original, side by side, treated as different things. The theorists who asked the question crowned. The experimentalist who answered it thanked. And the difference between being crowned and being thanked, like the difference between a left hand and a right hand, turns out to be permanent. Before we get to how the prize was decided, I want to slow down on what the result actually did to physics, because the speed of the Nobel only makes sense once you see how fast and how completely Wu's measurement rebuilt the theory of one of the four forces of nature. This is the part that should make the omission harder to swallow, not easier, because her experiment was not a confirmation of a finished idea. It was the foundation that an entire new theory of the weak force was poured on top of within months by some of the most celebrated theorists of the century. When Wu told Li that the asymmetry was nearly -1, the maximum, she was handing him more than a yes. The size of the effect was itself a clue, and it pointed straight at the nature of the neutrino. Within weeks of the result, the theoretical physicist Lev Landau in the Soviet Union, and Li and Yang, and the Pakistani physicist Abdus Salam, all independently developed what became known as the two-component theory of the neutrino, the idea that the neutrino is a fundamentally one-handed object, existing only in a left-handed form, its mirror twin simply absent from nature. The maximal asymmetry Wu measured was the experimental fingerprint of that one-handedness. She had not just shown that parity was violated, she had shown that it was violated as completely as it possibly could be, and that total violation was the door into the real structure of the weak interaction. And then, over the following year, the theory of the weak force itself was rewritten. In 1957, the physicists George Sudarshan and Robert Marshak proposed a specific mathematical form for the weak interaction, built to incorporate the handedness that Wu had found, a structure that came to be called the V-A theory. for the way it combined two mathematical objects called the vector and axial vector currents, with a relative minus sign that encoded the left-handedness. In 1958, Richard Feynman and Murray Gell-Mann published their own version of essentially the same theory, and it was their names that the formulation mostly came to carry, which is a small story of credit all its own that I will leave you to notice. The point is that the weak force, one of the four fundamental ways anything in the universe interacts with anything else, was given its modern mathematical shape in the 18 months after Wu's cobalt experiment, and that shape was built around the asymmetry she measured. The left-handedness was not a footnote to the theory. It was the load-bearing beam. It went further than that, and into territory that touched the deepest project in 20th century physics. The recognition that the weak force is intrinsically left-handed became one of the cornerstones of the effort to unify the weak force with electromagnetism into a single framework, the electroweak theory, developed through the 1960s by Sheldon Glashow, Abdus Salam, and Steven Weinberg, who shared the Nobel Prize for it in 1979. That unification, one of the great triumphs of modern physics, the theory that predicted particles, later found at CERN, and that sits at the heart of what physicists now call the Standard Model, has the handedness Wu discovered written into its foundations. You cannot build the Standard Model of particle physics without the fact that the weak force prefers the left hand, and that fact entered physics through a frozen speck of cobalt in a government laboratory, measured by a team of 5 people working in shifts against a clock that gave them minutes at a time, led by a woman whose name is on none of the prizes that the theory built on her. Result went on to win. Here is the pattern, and I want to name it directly because naming it is the only honest thing to do with it. The question of whether parity is conserved was asked by theorists, and they were crowned for it. The theory of the weak force that Wu's result made possible was built by theorists, and they were crowned for it. The unification that her handedness anchored was achieved by theorists, and they were crowned for it. There is a prize for asking whether the mirror is broken, and a prize for writing down the equations of a broken mirror universe, and a prize for fitting that universe into a larger theory. There is no prize for the person who actually went into the cold and caught the universe breaking the mirror with her own instruments. The discipline found a way to honor every layer of thought that surrounded her measurement, above it and below it, and to either side of it, and left a single experimentalist-shaped hole in the exact center where the measurement itself sat. That is not an accident of timing. That is a statement made over and over by a field about which kind of knowing it considers worth a medal. I want to be careful here, more careful than the simple version of this story usually is, because the question of why Wu was left off the prize does not have one clean answer. And the people who insist it was pure and simple discrimination are reaching past the evidence, and the people who insist it was a perfectly defensible decision are reaching past it in the other direction. The honest version is more uncomfortable than either, because it does not let anyone off the hook, and it does not hand you a villain. Let me give you the actual arguments, the real ones that real physicists and historians have made, and then let me tell you where I think the weight comes down. The first argument for the defense is about the Nobel rules, and it is not nothing. According to the rules as they were applied, and as a former secretary of the Nobel Committee named Anders Barani has explained, the work recognized by a given year's prize is supposed to have been published before that prize year. Li and Yang's paper, the theoretical work, was published in October of 1956, which made it eligible for the 1957 prize. But all 3 of the experimental papers, Wu's included, were published in early 1957. By a strict reading of the rule, no experimentalist was technically eligible to share the 1957 prize at all, because their published work did not yet exist in the prior year. On this reading, the speed that crowned Li and Yang is the very thing that excluded Wu. The prize came so fast that it could only reach the theory because the experiment had not yet been in print long enough to qualify. If you wait a year for the experiment to age into eligibility, you lose the chance to give the theorists a prize while the discovery is fresh. There is a genuine structural bind here, and it is worth naming honestly. The second argument for the defense is the one about the three experiments. Parity violation was confirmed nearly simultaneously by three groups: Wu and her Bureau of Standards collaborators, Garwin and Lederman and Weinrich, and Friedman and Telegdi. Some physicists at the time felt that singling out one experimentalist from among three groups would have been arbitrary, and some went further and felt that once Li and Yang had proposed the test, carrying it out was, in the phrase that gets used, known technique. The physicist Valentine Telegdi, who ran one of the three experiments, said bluntly that he did not think anybody among the experimentalists deserved the Nobel Prize very much in this case. The physicist Val Fitch noted that while Wu often gets the credit, the other groups were very important and it would not have happened without them. And in 1997, the physicists Nicholas Curti and Christine Sutton argued in print that the Bureau of Standards experiment was a collaborative team effort, the implication being that singling out Wu would slight the four men who worked beside her. And the most thorough version of the skeptical case comes from the chemist and historian Magdolna Hargitay, who looked hard at Wu's entire life and career and concluded in a piece for Physics World that to call her exclusion an injustice is an oversimplification of a complicated story. Hargitay's point is not that the snub was good. It is that Wu's career, taken as a whole, does not look like the career of a woman being systematically held down. She rose to the top of her field. She accumulated honors. She was respected and even feared. Hargitay writes that there is no indication in Wu's life suggesting the kind of discrimination the popular narrative requires, and that quite the contrary, Wu was celebrated. That is a serious historian making a serious argument, and I am not going to wave it away, because waving it away is exactly the kind of thing this channel exists to not do. So that is the case for the defense. Eligibility rules, 3 experiments, team effort, a celebrated career. Now let me tell you why I think, when you weigh all of it, the scale still comes down hard on the side of an injustice, just not the simple injustice the popular story tells. Start with the method, because everything the defense says about known technique collapses on this single point. It was Wu who proposed the cobalt-60 experiment, not Li, not Yang, not the field. The idea that the experiment was just turning a crank that the theorists had already designed is simply false on the historical record. Li and Yang proposed, in general terms, that aligned nuclei might be used. Wu is the one who specified cobalt-60, the demagnetization method, the entire physical architecture, but worked. The physicists who dismissed it as known technique, like Telegdi, may not have known that the technique itself was her contribution. Yang knew. He credited her with a deep perception of why parity had to be tested, and that perception was not a manual skill. It was the conceptual bridge between an open question and an actual answer, and it was hers. Now bring in the numbers, because this is where the defense's strongest argument, the eligibility rule, quietly falls apart. The eligibility rule only explains 1957. It explains why she could not have shared the very first prize. It says nothing about the next year, or the year after that, or the 16 years that followed. And here is what the recently opened Nobel archives reveal. Because the committee keeps its nominations secret for 50 years, and the records for this period have only lately come into full view. Chien-Shiung Wu was nominated for the Nobel Prize 23 times, 23, by 18 different physicists. Over the years, from 1958 to 1974, her name reached the committee in 10 of those 16 years. In 1971 alone, she received 6 separate nominations. Her champions included Nobel laureates of the first rank, men like Willis Lamb and Polycarp Cush, and her old mentor, Emilio Segre. The physics community, over nearly 2 decades, told the Nobel Committee again and again and again that this woman deserved the prize. And the committee, year after year after year, said no. The eligibility rule cannot survive that. You cannot explain 23 nominations across 16 years with a technicality about publication dates in a single year. Whatever kept her off the prize in 1957, something else kept her off it in 1958 and 1965 and 1971, when she was being nominated 6 times over and still passed by. The structural excuse explains the first refusal. It does not explain the next 22. And then there is a detail from those archives that I cannot stop thinking about, because it cuts straight into the human heart of the thing, of the people who nominated Wu. Tsung-Dao Lee, the man who had come to her office and asked her to find the answer, nominated her 3 times in 1964, 1971, and 1972. He tried to get her the prize. Ning, the other man who shared the prize her experiment had confirmed, never nominated her, not once. Now, I am not going to tell you what was in Yang's heart, because I do not know, and this channel does not psychoanalyze the dead, but I can tell you the fact, and the fact is its own kind of weight. One of the 2 men who stood in Stockholm and accepted the prize built on her work spent years trying to bring her up beside him. The other never put her name forward at all. And those 2 men, Li and Yang, would themselves stop speaking to each other around 1962, their partnership collapsing in a bitter dispute over credit and the order of their own names. A feud Yang would later call one of the great tragedies of his life. The discovery that the universe cannot tell its reflection from itself was made by people who spent the rest of their lives unable to agree on whose reflection was whose. The physicist Jack Steinberger, himself a Nobel laureate, did not equivocate about any of this. He called the omission of Wu the biggest mistake in the history of the Nobel Committee. Not a regrettable technicality, not a defensible call made under difficult rules, the biggest mistake the committee ever made. And Wu's other defenders, the people who actually watched it happen, did not treat it as a close case. They treated it as a wound. Here is what I think the truth is, as close as I can get to it. The exclusion from the 1957 prize, specifically, is partly explained by timing and rules, and the awkward existence of 3 experiments. That part of the defense holds, but the failure to ever honor her, in any of the 16 years she was nominated, by a committee that received 23 pleas from 18 physicists, including her own collaborator, is not explained by any of that. And once the structural excuses are exhausted, what is left is the harder and quieter thing, the thing Hargitay is right to say cannot be proven, and wrong, I think, to dismiss. A woman, an immigrant, an experimentalist in a field that prized theorists, working in an era that did not equalize her pay with her male colleagues at Columbia until 1975, almost 20 years after she broke Parity, found that the door to the highest recognition in her field stayed shut, no matter how many times the people who understood her work knocked on it. You do not need a conspiracy to explain that. You need only the ordinary machinery of who a profession finds it easy to imagine as a laureate. and who it does not. Wu herself rarely spoke about it in public, and when she did it with a restraint that is somehow harder to read than anger would have been. In a private letter, she allowed herself one line that drops the guard. She wrote that, although she had not done her research for the prize, it still hurt her a great deal that her work had been overlooked. It still hurt her a great deal, that is the whole of it, from the person it happened to. Not a denunciation, just the admission that it hurt, and that it kept hurting. Her most quoted public remark on the broader question of being a woman in physics came at a symposium at the Massachusetts Institute of Technology in October of 1964, and it is sharper than it first appears. She asked whether the tiny atoms and nuclei, or the mathematical symbols, or the molecules of DNA, had any preference for either masculine or feminine treatment. It sounds like a gentle rhetorical question. It is actually a scalpel. She was pointing out that the physics does not care about the sex of the person doing it, that nature hands out its secrets without checking who is asking, and that therefore any barrier between a woman and the recognition of her work is a human invention laid on top of a universe that has no such barrier. The atoms do not discriminate. Only the people who study them do. And the woman saying this had just spent a decade watching exactly that gap between what the atoms gave her and what the people gave her play out in her own life. And the pattern she sat inside was not hers alone, which is the part that turns a single injustice into something structural enough to make you genuinely angry. Count them. Lise Meitner, who worked out the theory of nuclear fission and watched the 1944 Nobel in chemistry go to her collaborator, Otto Hahn, alone, and who was nominated dozens of times across her life, and never won, and who has an element, Meitnerium, named after her as a kind of consolation the prize never gave. Rosalind Franklin, whose X-ray work was essential to the discovery of the structure of DNA, who died before the 1962 Nobel went to Watson and Crick and Wilkins, and whose data made their model possible. Jocelyn Bell Burnell, who as a graduate student discovered the first pulsars in 1967 and watched the 1974 Nobel for that discovery go to her supervisor. 4 women, 4 foundational discoveries, 4 prizes that went to the men around them. You can argue any one of these cases on its particular merits. The defense can find a technicality for each, but the pattern does not care about the technicalities, and the pattern is the indictment. When the same outcome arrives over and over for the same kind of person, the explanations start to sound less like reasons and more like the alibis of a system describing its own behavior. That is the broken symmetry of credit. And I have spent this long on it because I think you cannot feel the ending of this story properly until you have felt the injustice of it fully, because the two halves are about to fuse. Wu proved that the universe has a preferred hand. The Nobel Committee proved that physics has a preferred kind of person. And the deepest and strangest part of the whole thing is what the universe's preferred hand actually turns out to mean. Once you stop looking at the politics and follow the physics all the way down to where it touches you. Because the handedness she found does not stay in 1957. It does not stay in the cobalt. It reaches forward in time to the present moment and downward in scale into the molecules you are made of. And it raises a question about your own body that physics still cannot answer. Start with the alien, because it is the cleanest way to feel how large this is. There is a puzzle that the writer and mathematician Martin Gardner laid out in a book called The Ambidextrous Universe. A puzzle he traced back through William James all the way to the philosopher Immanuel Kant. And it is called the Ozma problem. Imagine you have made radio contact with an intelligent civilization somewhere far across the galaxy. You can exchange any information you like, any mathematics, any physics, any description of the laws of nature. You build up a shared language of science, and then you try to tell them what you mean by the word left, not which of your hands you call left. They cannot see your hands, the actual concept, the thing that distinguishes a left-handed glove from a right-handed one. Try to define it using only words and laws that you both already share. Before 1957, this was impossible, and not as a matter of difficulty, but as a matter of principle. There was no way to do it. Every law of physics you could send them, every equation, was perfectly symmetric between left and right. You could describe gravity, electromagnetism, the strong force, all of it, in complete detail, and none of it would single out one hand. If you said, do this and you will produce a left-handed thing, the mirror image instructions would produce a right-handed thing with exactly the same validity. And nothing in the laws would tell the alien which one you meant. Left and right were, in the deepest sense, undefinable across any gap where you did not already share a physical object to point at. Two civilizations could agree on every law of nature in the universe and still have no way to know whether they were mirror images of each other. Wu's experiment ended that. After 1957, you can do it. You tell the alien to take a cobalt-60 nucleus, align its spin, and watch the beta decay. The electrons come out preferentially against the spin. Now you say, curl the fingers of a hand in the direction the nucleus spins, and the thumb that does not point the way the electrons go, that thumb defines left. It works. It works anywhere in the universe for any civilization, with no shared object required, because the asymmetry is built into the weak force itself, and the weak force is the same everywhere. For the first time in the history of thought, left and right became absolute, definable, real, communicable across any distance, because the universe itself had been caught making the distinction. That is what Wu actually did. She did not just find a quirk in radioactive cobalt. She converted left and right from human conventions into features of reality. She gave the words a meaning that does not depend on us at all. And once you start pulling on that, it gets worse, in the specific sense that the asymmetry is not a small correction the universe makes around the edges. It is total. Remember that the asymmetry parameter came out close to -1, the maximum. The weak force does not slightly prefer one hand. It is built almost entirely out of one hand. And the cleanest place this shows up is in the particle that haunts this whole story underneath the surface, the neutrino. The neutrino is the ghost of physics, a particle so reluctant to interact with anything that trillions of them are passing through your body every second, streaming out of the sun and through the earth, and through you as if you were not there, and almost none of them touch a single atom of you on the way. It is produced in beta decay, the same process Wu studied. And here is the thing that parity violation forced physics to confront about it. The neutrino appears to come in only one-handedness. Particles have a property called helicity, which relates the direction of their spin to the direction of their motion, a kind of intrinsic left or right-handedness to the particle itself. And every neutrino ever observed has been left-handed. Its antimatter partner, the antineutrino, has always been right-handed. A right-handed neutrino has never been detected. Li, when Wu told him the asymmetry was nearly -1, recognized it instantly as the signature of what was called the two-component theory of the neutrino, the idea that the neutrino exists in only one-handed form. The universe did not merely lean toward one hand in this corner of physics. It declined to build the other hand at all. There is a particle in nature that comes in left, but as far as anyone has ever been able to measure, simply does not come in right. I want to stop and make sure the strangeness of that lands, because it is easy to let it slide past as a technical fact. We are not talking about a preference. We are talking about an absence. Somewhere in the foundations of reality, there is a missing reflection. The right-handed neutrino is the thing that should be there, the mirror twin that every symmetry of the old physics demanded must exist. And it is not there. The mirror does not just distort. In places, it shows nothing at all. And nobody knows why. That is the question that sat unanswered when they drank the wine from paper cups. And it is the question that sits unanswered now. Why is the weak force left-handed and not right-handed? Why this hand? There is no known law that requires it. The universe made a choice that nothing forced it to make. At the beginning, once, and it has held to that choice through every event since. And physics can describe the choice in exquisite detail and cannot tell you the first thing about why it was made. We have a complete account of what the universe prefers, and not a single sentence about why it prefers it. This is the place where the language of physics starts to strain, where careful people who would never indulge in mysticism find themselves reaching for words that sound almost like description of a will. The universe prefers. The universe chooses a hand. The universe declines to build the mirror twin. I am using those words deliberately, and I want to be honest about why. They are not literally true. The universe does not have preferences the way you do. But the reason physicists keep reaching for that language is that the alternative, the bare statement that a fundamental asymmetry exists for no reason and follows from no deeper principle, is somehow harder to sit with than the metaphor. It is easier to imagine a universe that chose than a universe that simply, brutally, is lopsided with no chooser and no reason. Wu found a fact that has the shape of a decision and none of the comfort of one. Something was decided at the root of physics, and there is no one to have decided it, and it cannot be undone, and we cannot explain it. And if all of that were the end, if parity violation were just a deep, strange fact about radioactive nuclei and ghostly particles, it would already be one of the most unsettling discoveries of the century. But it is not the end, because the broken mirror Wu found turned out to be the first crack in a larger structure of broken symmetries. And that larger structure runs directly into the single biggest question you can ask about why anything is here at all. The handedness of the weak force was not an isolated oddity. It was the loose thread. And when physics pulled on it over the next decade, the thing that unraveled was the explanation for why the universe contains matter instead of nothing. When parity fell, physicists did what physicists always do when a symmetry breaks. They went looking for a bigger symmetry to save. The reasoning went like this. Yes, the universe can tell left from right. The mirror is broken. But maybe a deeper symmetry survives if you do two things at once. Maybe if you reflect the experiment in a mirror and at the same time swap every particle for its antiparticle, turning matter into antimatter, then the combined operation would be symmetric even though each one alone is not. The mirror flip is called P for parity. The matter-antimatter swap is called C for charge conjugation. And the hope was that the combination, called CP, would be the real, unbroken symmetry of nature, the law that the universe actually obeyed even though it had abandoned the simpler one. It was an elegant retreat. The universe prefers a hand, yes, but perhaps a left-handed particle and a right-handed antiparticle are perfect mirrors of each other, and the deep symmetry is restored one level up. For 7 years that hope held, and then, in 1964, 2 physicists at Princeton, named James Cronin and Val Fitch, The same Fitch who had cautioned about giving Wu sole credit ran an experiment on a particle called the neutral kaon, and they found that CP is violated too. Not by much. The effect was tiny, a tiny asymmetry in the way these particles decayed, showing up in about 1 decay out of 500. But tiny was enough because it was not zero, and it was never supposed to be anything but zero. The deeper symmetry that was supposed to save the day was also broken. The universe does not just tell left from right. It tells matter from antimatter in a way that breaks the combined mirror as well. Cronin and Fitch won the Nobel Prize for it in 1980. And I will note in passing, because by now you will hear it the way I do, that the two theorists got the prize fast, and the experimentalists who actually found the broken symmetry got theirs 16 years later, which is its own small echo of a pattern. Now here is why that tiny asymmetry, 1 decay in 500, is one of the most important numbers in all of science, and why it connects the death of a cobalt nucleus to the reason you are able to read this sentence. In 1967, the Soviet physicist Andrei Sakharov, the same man who would later become famous as a dissident and win the Nobel Peace Prize, asked a question that the broken mirrors had made unavoidable. Why is there any matter in the universe at all? In the standard picture of the Big Bang, matter and antimatter should have been produced in exactly equal amounts, a perfectly balanced ledger, and matter and antimatter annihilate on contact, destroying each other completely and turning into pure light. So if the early universe had equal parts of each, they should have wiped each other out entirely, leaving a cosmos of nothing but radiation, no galaxies, no stars, no planets, no chemistry, no you. The fact that you exist, that anything made of matter exists, means the ledger was not balanced. There was a tiny excess of matter over antimatter, something like 1 extra particle of matter for every billion matter-antimatter pairs. And after all the annihilation finished, that 1 in a billion left over is everything. It is every atom in every star and every cell in your body. You are made entirely of the rounding error. And Sakharov proved that to produce that imbalance, to get a universe with more matter than antimatter, nature must satisfy 3 conditions. And one of those 3 conditions is the violation of CP symmetry. Without a broken mirror, without exactly the kind of asymmetry that the fall of Parity first revealed, the early universe would have stayed perfectly balanced and annihilated itself into nothing. The reason there is something rather than nothing is, in part, that the universe distinguishes its reflections from itself. The handedness Wu found in a frozen speck of cobalt is a member of the same family of broken symmetries that allowed matter to survive the first second of existence. Pull the thread that starts at the cobalt-60 nucleus, and it runs, through CP violation and Sakharov's conditions, all the way to the answer to the oldest question there is. Why is there anything? I have to be honest about a wrinkle here, because this channel does not hand you a clean victory the field has not actually earned. The amount of CP violation that physicists have so far measured, the kind that lives in the established theory called the Standard Model, appears to be far too small to account for all the matter in the universe. By the most careful estimates, the known broken mirrors can explain only a tiny fraction of the matter that survived, which means that somewhere out there is more broken symmetry than we have found, a deeper asymmetry that physics has not yet located, doing the heavy lifting of bringing a material universe into being. The broken mirror Wu, found in 1956, was the first one. It was not the last, and it was not even close to big enough. There are more cracks in the mirror than we can yet see, and we know they have to be there only because we are here to know it. We are the evidence that the mirror is more broken than physics can currently explain. So, follow the chain once, slowly, because the framework I am working from is right that this kind of chain is where the weight actually lands. A theorist asks in a library in 1956 whether anyone ever checked an assumption. A woman cancels a trip home she has waited 20 years for and freezes a speck of cobalt to 3/1000ths of a degree above the bottom of the universe and watches it choose a side. That choosing is the first visible crack in the mirror of reality. The crack widens. By 1964, the deeper mirror is broken too. By 1967, a physicist realizes that this exact kind of brokenness is the reason matter outlived antimatter in the first instant of time. And the matter that outlived is the matter you are made of. The broken mirror is not a curiosity in a textbook. It is the reason the textbook and the hands holding it and the eyes reading it are here at all. Every atom in you is a survivor of an annihilation that should have left nothing. And the only reason there was a survivor is that the universe at the root is not symmetric. And now we have arrived at the place I have been telling you we would arrive at since the very beginning. The place where the handedness stops being about distant particles and the birth of the cosmos and becomes about the specific arrangement of the molecules inside your own body. Because the universe is not the only thing that has a preferred hand. You do. Every living thing does. And whether those two preferences, the universe's hand and life's hand, are the same broken mirror seen twice, is a question that runs straight off the edge of what anyone can currently prove. The molecules of life come in left-handed and right-handed versions, exactly the way your hands do, and for exactly the same reason. A molecule can be built from the same atoms connected in the same order and still come in two forms that are mirror images of each other and cannot be superimposed no matter how you rotate them. Chemists call this chirality, from the Greek word for hand, and it was Louis Pasteur who first saw it in 1848, peering at crystals under a microscope and noticing that some were the mirror images of others, and painstakingly sorting them apart with tweezers. The two mirror forms of a molecule are called enantiomers. In every way you can measure them in isolation, they are equally stable, equally probable, equally real. If you build a molecule in a laboratory from scratch, with no living thing involved, you get both hands in equal amounts, a 50-50 mixture, because nothing in ordinary chemistry prefers one over the other. Both hands are allowed, and both hands show up. Except in you. Except in every living thing that has ever existed. Life does not use both hands. The proteins in your body are built from amino acids, and amino acids are chiral. They come in left-handed and right-handed forms, and life uses only the left-handed ones, almost without exception. Every protein in you, every enzyme, every strand of muscle is assembled from left-handed amino acids, and never the right-handed ones are chemically just as good. And the sugars run the other way. The backbone of your DNA, the sugar that gives the double helix its structure, is right-handed, and life uses only the right-handed sugar, never the left. Your entire biochemistry is single-handed. It is, in the literal language of chemists, homochiral, one hand all the way down. Pour a perfect 50-50 mixture of both forms into a cell, and the cell will use only its preferred hand and ignore the other, the way a glove fits only the hand it was made for. This is one of the genuine unsolved problems in the science of how life began, and I want to be precise about why it is a problem rather than just a curiosity. If both hands of every molecule are equally stable and equally likely to form, then the chemistry that preceded life should have produced both in equal amounts a balanced soup, a 50-50 world. And yet, Life, when it emerged, came out built, from one hand only, and locked. So something, at some point, broke the balance. Something tipped the early chemistry of the world, or of whatever rock or pool or comet life first stirred in, away from 50-50 and toward the single-handed arrangement that every cell on Earth has inherited ever since. The question of what tipped it is called the problem of biological homo-chirality, and it has been argued over for more than a century, and it is not solved. Now, you can probably feel where this is going, because the parallel is almost too clean. There is a fundamental asymmetry in the universe, discovered by Wu, that prefers one hand, and there is a fundamental asymmetry in life that prefers one hand. And the obvious, irresistible question is whether the second is caused by the first. Whether the reason your proteins are left-handed traces back through some chain of chemistry to the same broken mirror in the weak force that Wu found in her frozen cobalt. Whether the handedness of the universe printed itself onto the handedness of life. That hypothesis is real, and it has a name, and it was proposed almost immediately after Parity fell. In 1959, just 2 years after Wu's experiment, the physicists Frederick Vester and Thilo Ulbricht suggested that the parity violation of the weak force could be the origin of life's handedness. The mechanism they imagined runs roughly like this. The electrons thrown out in beta decay, the same kind of electrons Wu was counting, are themselves preferentially one-handed because of parity violation. These one-handed electrons were everywhere in the early Earth, streaming from natural radioactive decay. And if those handed electrons interacted even slightly differently with left-handed and right-handed molecules, they could, over enough time and enough material, tip the balance, destroying one hand a touch faster than the other, leaving a faint excess of the survivor that life then locked in and amplified. The universe's broken mirror, transmitted through radioactive decay into the chemistry of the first molecules, choosing life's hand for it. It is one of the most beautiful ideas in science, a single asymmetry born at the foundation of physics, propagating upward to every level of reality until it reaches the shape of the proteins that let you hold a thought. And here is where I have to do the thing this channel exists to do, which is tell you the truth, even when the truth is less satisfying than the beautiful story. The Vester-Ulbricht hypothesis is, as of right now, not confirmed, and most of the scientists who have studied it hardest are skeptical. There is a real physical effect underneath it. The parity violation of the weak force does mean that a left-handed molecule and its right-handed mirror twin are not perfectly equal in energy. One of them is very, very slightly more stable than the other. This difference has a name, the parity violating energy difference, and physicists have calculated its size. And the size is the problem. It is staggeringly small. The energy difference between the two hands of a molecule is on the order of 1 part in 10 to the 17th power of the thermal energy jostling those molecules around. To give you a sense of that, it corresponds to an excess of something like 1 molecule out of every 600 quadrillion, a bias of 1 in 600 million billion. That is the thumb the weak force puts on the scale of chemistry, and it is so light that for most chemists, it vanishes against the roar of ordinary thermal noise. The chemist William Bonner spent something like 2 decades of his career chasing exactly this question, running experiments to see whether handed radiation could bias molecular chirality, wanting it to be true the way you want a beautiful idea to be true. And in the year 2000, after all of it, he wrote a sober assessment, concluding that consideration of all the lines of evidence leads to the conclusion that there is no substantiation for a causal connection between the parity violation of the weak force and the handedness of life, and that the two levels of asymmetry appear to be entirely independent of each other. That is one of the people who most wanted the link to be real, telling you, after a lifetime of looking, that he could not find it. There are dissenting results. In 2014, physicists named Ning and Gay reported a small-handedness-dependent effect in how electrons broke apart certain molecules, a flicker of the kind of asymmetry the hypothesis predicts. But the mainstream verdict remains that the weak force is, at best, a very weak explanation for why life is single-handed. Because the bias it provides is so absurdly tiny that getting from it to the total homo-chirality of life requires an amplification mechanism that nobody has convincingly demonstrated. So here is the honest state of it, and I think the honesty is more unsettling than a clean answer would be. We know the universe has a preferred hand. We know life has a preferred hand. We know there is a real physical mechanism by which the first could, in principle, have caused the second, and we do not know whether it did. The link might be there, faint and amplified across 4 billion years into the biochemistry of everything alive. Or the two asymmetries might be a coincidence, two unrelated broken mirrors that happen to rhyme. The universe lopsided for its reasons, and life lopsided for its own entirely separate ones. Nobody can currently close the gap. You are made of a single hand of molecules, and when you ask why that hand and not the other, you get the same answer you get when you ask why the weak force chose left instead of right. The honest answer is that we do not know. The asymmetry is real, the asymmetry is total, and the asymmetry has no explanation anyone can give you. The question that hung in the air over 5 people drinking wine from paper cups in 1957 is the same question that hangs over the arrangement of the proteins in your hand as you hold this. Why this way? Why not the mirror? And there is no one to ask and no answer on file. Wu did not stop after Parity, and the honors did come, which is the part of the story that lets some people argue she was treated fairly in the end, and which I think actually sharpens the wrong rather than softening it. She became a full professor at Columbia in 1958, the first woman ever tenured in the university's physics department. She was elected to the National Academy of Sciences. In 1975, she became the first woman to serve as president of the American Physical Society, the professional body of American physicists. She received the National Medal of Science. Her textbook on beta decay, published in 1965, became a standard reference that physicists relied on for decades. An asteroid was named after her, the first time a living scientist had been so honored. There is a road at the CERN laboratory in Europe called Route Wu. She was called the First Lady of Physics, the Chinese Madame Curie, the Queen of Nuclear Research, and the physicist Isidore Rabi reportedly ranked her experimental contributions above those of Marie Curie herself. And in 1978, she received the very first Wolf Prize in physics, an award created in part, and this is not my interpretation, but the widely understood purpose of it, to honor scientists who deserved a Nobel Prize and did not get one. Think about what it means to be given the inaugural version of a prize whose unofficial reason for existing is to console the people the Nobel Committee passed over. It is recognition, shaped exactly like the recognition that was withheld, a medal in the form of an apology that the institution which owed the apology never made. She accepted it. She had every reason to. But there is no version of that award that is not also a statement about the one she never received. The same year, she could finally collect prizes like that one was. By the cruel arithmetic of her life, decades after the door home had closed, she was not able to return to China until 1973. By then, both her parents were dead. The graves had been destroyed in the convulsions of the Cultural Revolution. the same upheaval that had killed a brother and an uncle. She had traded the trip home in 1956 for the chance to break Parity before anyone else could, and when the trip finally became possible, there was almost nothing left at the other end of it to come home to. The wall she had spent her adult life on the wrong side of did eventually lower, and by the time it did, the people it had separated her from were gone. She kept working, kept teaching, kept her ferocious standards, kept insisting on being addressed by her own name rather than her husband's. Her pay at Columbia was not equalized with her male colleagues until 1975, almost 20 years after she had performed one of the defining experiments of the century, which tells you something about how long the ordinary, unglamorous version of the asymmetry persisted right alongside the prestigious version. She died on the 16th of February 1997 in New York City of a stroke at the age of 84, and her ashes were carried back across the ocean she had crossed as a young woman in 1936, and they were buried, according to her wishes, in the courtyard of a school. Not just any school, the Mingde School, the one her father had founded, the school for girls, the deliberate act of inclusion that had given a girl in a small town near Shanghai the conviction that her mind was worth developing. She began inside her father's refusal to accept that girls did not need to learn, and she ended there, in the same courtyard, having proven something about the universe that the highest institution in her field could not bring itself to fully credit her for. I told you at the start to hold your hands up and look at them, and I want to come back to that now, because the image carries more than it did an hour ago. The thing that makes your left hand a left hand and not a right hand is real. Wu proved it is real. It is not a convention, not a human label laid over an indifferent world. The universe itself observes the distinction, built it into the weak force at the beginning, and has held to it ever since, for reasons that nothing in physics can supply. Your two hands are mirror images that cannot be made the same. And the reason that difference is permanent goes all the way down, past your hands, past the cells in them, past the left-handed proteins those cells are spun from, down into a broken symmetry at the root of reality that a woman first saw in the death of a frozen atom, and that no one has ever been able to explain. And the woman who saw it spent her life on the wrong side of a different mirror, one that physics built, and physics could have unbuilt, and chose, year after year, 23 nominations across 16 years. Not two. There is a way of looking at this whole story in which the two broken symmetries are not a metaphor for each other at all, but the same kind of fact seen at two different scales. And I have gone back and forth on whether that way of looking at it is profound or just a trick of language. And I still do not fully know. So let me lay it out and let you sit with it the way I have had to. The universe has a preference it cannot justify. It prefers one hand in the weak force, left over right. And it built an entire particle, the neutrino, with only the left hand and no right-handed twin. And when you ask physics why, physics has no answer, not a partial answer, not a contested answer, no answer. The preference is total. It is foundational. It has been there since the first instant, and it follows from no deeper law that anyone has ever found. It is, as close as the word can be applied to the cosmos, arbitrary. The universe decided, and there is no record of the reasoning, because there was no reasoning, because there is no one who reasons. Something was chosen, and nothing did the choosing. And then there is the other preference, the human one, the one that kept a woman's name off a prize her work made possible and kept it off for 16 more years, through 23 nominations from 18 physicists, one of whom was the man who had asked her the question in the first place. That preference is not arbitrary. That is the difference, and it is the part that should keep you up. rather than the cobalt. The universe's lopsidedness has no reason, and so you cannot be angry at it, you can only stand under it and feel small. But the field's lopsidedness has reasons, legible ones. The ordinary reasons of who an institution finds it easy to picture wearing the medal and who it does not. And reasons can be examined, and reasons can be changed, and these reasons were not. The broken mirror in the weak force is a fact you have to accept. The broken mirror in the credit is a fact someone could have fixed every year for 16 years by writing a different name on a card and chose not to. One of these asymmetries is the universe being what it is. The other is people being what they decided to be. I keep returning to the missing particle, the right-handed neutrino, the mirror twin that every old symmetry said had to exist and that has never once been detected. And I keep thinking it is the truest image in the whole story. Physics went looking for the reflection that the rules demanded, the matching half that would make the world symmetric again, and it was not there. The slot was empty. The universe had simply declined to build it. And there is a woman in this story who is the reflection the rules demanded and who was not there when the prize was given, whose slot on the medal was empty, who was thanked from the stage and left off the bronze. The neutrino is missing its right hand. The discovery is missing her name. I am not telling you those two absences are caused by the same thing. I am telling you they have the same shape, and that the shape is the thing this story is actually about. Reality is not symmetric. Neither is memory. And both asymmetries are permanent in the same brutal way your two hands are permanent, the way no rotation will ever lay one over the other. Think about where you are sitting right now, because the framework I have been following is right that the only ending that earns its weight is the one that reaches you. Trillions of neutrinos are streaming through your body as you take this in, pouring out of the sun, passing through the earth, and through you without touching almost anything. And every single one of them is left-handed, because the universe declined to make the other kind. The proteins holding your body together as you sit there are left-handed, every one of them. And the sugar in the DNA inside every cell is right-handed, every strand, and you are single-handed all the way down for reasons that might trace back to that same broken mirror, or might be a separate accident that only rhymes with it, and no one alive can tell you which. The atoms you are made of are the 1 in a billion remainder that survived an annihilation at the beginning of time. And they survived only because the early universe could tell matter from antimatter in a mirror, which is a broken symmetry from the same family as the one Wu found. You are, in the most literal physical sense available, a structure built out of broken symmetries, made of the leftover that asymmetry spared, assembled from a single hand of molecules, shot through every instant by one-handed ghosts. The lopsidedness is not out there in a cold government laboratory in 1957. It is the reason you have a body and the architecture of the body you have. And the question that was open in that laboratory is still open now. It did not get answered in the decades since. It got deeper. We learned that the asymmetry is total, that the neutrino has no right hand, that the deeper CP mirror is broken too, that the brokenness we can measure is not even enough to explain the matter we are made of, which means there is more of it out there that we have not found. Every layer of the answer was another door into a darker room. Why does the universe prefer this hand? We do not know. Why is there matter instead of nothing? Because the mirror is broken, but not by enough that we can account for it. Why are you built from a single hand of molecules? We do not know. And the most beautiful explanation, the one that would tie your proteins back to the foundation of physics, is the one that careful people cannot make work. The fall of Parity did not close a question. It opened a permanent one. And then it kept opening it wider. Chien-Shiung Wu cancelled the trip home she had waited 20 years for, and she went into the cold, and she became the first human being to catch the universe in the act of telling left from right. She did the thing the smartest physicists in the world bet against and lacked the imagination to chase. She converted left and right from human conventions into facts of nature that you could explain to a mind on the far side of the galaxy. And for proving that reality cannot tell its reflection from itself, she was placed by the people who should have known better on the wrong side of a reflection, thanked from the stage, named in the lecture, and left off the prize year after year, while one of the two men beside her tried to bring her up, and the other never spoke her name to the committee at all. She was buried in the courtyard of the school her father built so that girls could learn. The universe she spent her life reading still has not explained its preference for one hand. And it never will, because there is nothing to explain, and no one who chose. The choosing in this story, the only choosing, the kind that has reasons and could have gone the other way, was done by people. They are the ones who picked a hand. They are the ones who could have picked again every year and did not. The mirror in the weak force was broken before the first star formed and cannot be repaired. The other mirror was broken in Stockholm by a decision, and it could have been mended at any moment with a single name. And the moment passed and passed and passed until there was no one left to hand the medal to. Reality prefers a hand. So did they. Only one of them had a reason, and it is the one with the reason that should disturb you.